Yeah, thank you very much, organizers and attendees. Yes. So I've been asked to talk about drought monitoring, but what exactly I need to talk, I think I'm not that clear because there are a large number of participants with the varying background and varying level of experience. I was trying to see that what kind of exercise you are doing. But in my presentation, I will remain a little bit broad. I will talk the basic concepts and some of the applications and also present EC mode's work during this time. I hope it is not very targeted to all the audience, but hope the conversation will be useful to understand the drought monitoring mechanism applications, in particularly in South Asia and Hindu Kush Himalayan region. So starting with my giving a background of my institution, I assume that EC mode has already been introduced in the opening session. Within EC mode, we have an initiative called Survey Hindu Kush Himalayan region, where we are collaborating with NASA and national agencies to promote use of Earth observation for societal benefit. We also call it connecting space to village. So we are working in four broader areas, which includes water and disaster, weather and climate, land cover and ecosystem services. And one of the more very important areas is agriculture and food securities. So our aim under this survey HKH is to improve the access to the data, tools, and models to the scientific community, strengthen capacity of national agencies in use of Earth observation data systems, and also create some of sort of like tailored decision-making tools so it can be easily used by decision makers so they do not have to go through laborious data processing which you are trying to do a while earlier. And then also an overarching objective is to foster transboundary cooperation. We know that data exchange is a complicated issue, but earth position data is available across the boundaries and most of the time open access. So if we talk about use of earth observation in survey program, particularly for agriculture and food security, we have a framework where we have science available in form of technologies as well as in form of products. Like we are using earth observation technology, meteorological science, crop modeling, and some of the earth observation data products observed through satellite remote sensing is soil moisture, ET, crop stress, and kind of things. We take those technology, we engage with stakeholders like national ministries and global institutions like World Food Program or CIMMYT, and then we co-develop the solution in the form of advisories or assessment. So far, we have been working on crop area estimation, rainlands monitoring, food security assessments, drought outlook. We are also looking for some avenues to work on crop insurance as well. So that was the institutional background and how we are engaged in use of earth observation for crop monitoring and drought assessments. But coming back to drought particularly, if we see then the geographic area where we work is Hindu Kush Himalayan region, and if we see that drought is one of the major catastrophe both in economic terms as well as social vulnerabilities. So we get more news about floods, but if you see that economic losses are about more than 60% occurring from drought. So that's sort of a mostly known as a silent killer and silent disaster, which we need to talk more about, and we need to put more attention to address those catastrophes. Again, when we are talking about drought and this risk management, we can look into three pillars. One is monitoring and early warning systems. Then the other is looking into the vulnerability, like if there is enough capacity of local systems to deal with that or resilience, and that is a second pillar, that identifying the vulnerabilities of the communities. Then third is this mitigation response. So this is a broad sphere of activities. Today we will be mostly talking about monitoring systems, but we'll also be touching some way on the resilience as well as mitigation response. Some of the examples where drought monitoring systems help in response planning, as well as looking at the resilience of the local systems. Coming back to, if we need to monitor a particular area or a subject or indicator, we need to know what exactly it is. Drought has different definitions. There are operational definitions, there are conceptual definitions, and conceptual definitions mostly deals with the impact, but operational definitions are needed to monitor the different variables. On operational definitions, we have 3 to 4 categories: meteorological drought, agriculture drought, hydrological drought, and socioeconomic drought. Meteorological drought is directly related to percentage of precipitation. Hydrological drought comes when deficit in a particular area, deficit in precipitation in a particular area, when it impacts the agriculture, it is known as agriculture drought. Then when it also touches the water use at household level, or deficiency in river streams, is known as hydrological drought. But then overall impact on the society in terms of discrepancies in livelihood, or individual levels livelihood, or economic impact on the country, is considered as socioeconomic drought. So I will not get into this more detail. This is the, like, one particular instance leads to another, and the further areas. And when we are talking about water availability, like on the planet Earth, water is constant. So what is climate systems or earth systems are actually uh, making that water movement, and making deficit in one place and then abundance in other place. So we need, like, this is water availability in terms of drought is tightly linked with earth systems and climate dynamics. That is very important to understand. Again, coming back to, since this particular lecture is more focused on monitoring, so it is very important that we identify the indicators to monitor a particular phenomena. In case of drought monitoring, there are key indicators which are important in one geographic area or another geographic area. That starts from rainfall, snowpack, soil moisture, temperature, stream flows, groundwater, and reservoir ET and vegetation stress. Like, for example, rainfall is, if I talk about HKH region, rainfall is particularly important in countries like Nepal, where monsoon rainfall is like, the summer rainfall is the major source, and partially there's also dependent of agriculture on glacier melt. But if we go into the western regions, like for in Afghanistan and western parts of Pakistan, a large part of irrigation system are dependent upon snow accumulation, and then it's melt in the spring and summer season, and so on. Then soil moisture, temperature are later indicators to look at the drought conditions. And when we talk about indicators, then what is drought monitoring? We associate a threshold value to a particular indicator. So those threshold values can be set in terms of percentage of normal, or that is the simplest form of setting up the threshold values. But then again, there are some complex systems to develop composite drought indices as well. Now, why we are talking about particularly this training is about Earth observation. So here it is important that due to the complexity of nature of monitoring those precipitation, soil moisture, snow accumulation, an intensive investment on putting the ground stations. Remote sensing is a good substitute to monitor those indicators through satellite observations. If I talk about indicator, like we have quite good means to observe precipitation through satellite, soil master to certain extent, snow cover, vegetation, ET, and to a limited extent, groundwater as well. But groundwater is mostly evaluated over longer period of time and at continental scale. So it's not that good. Then again, it's very important that at what detail we are in position to monitor those observations. So it varies from variable to variable. Precipitation at this point of time, uh, uh, operational systems are available at 5 kilometer resolution. Soil moisture varies from 5 kilometer. If you have a downscale data, it is possible to do it 5 kilometer, but otherwise direct satellite observations are only available at 25 kilometer. Snow cover can be seen at 250 meter. Vegetation is particular drought indicator. Vegetation condition is particular drought indicator, which can also be seen at farm level. So that's one. I'll go through it at the later stage. Again, ET is a coarser 1 kilometer to like 5 kilometer to 1 kilometer resolution data is available. Again, groundwater is only for continental scale at a very coarser resolution of 100 kilometer. So I mentioned that the if we communicate all those quantities to higher level decision makers, like this particular season, we are going to receive 300 millimeter of water. So for a decision maker who is not like into this quantitative water assessment, it doesn't provide an actionable information. So what we try to do, we try to develop indices that we can be like we can in communicate a simple a situation in a very simple manner. Like for example, a GDP is like one sort of index which communicate about poverty or wealth in a particular community or a country very conveniently. Similarly, for drought monitoring or any kind of like water resource assessment and communication, there are like indices are developed so that we can communicate a situation in a very simple way. So the some of the attributes of indices that it can communicate a complex situation in a simple manner. It also gives it is a qualitative in nature, but it also gives some sort of quantitative information. And then they are mostly built on the historic reference. So like for example, in one particular farm, if rice is cultivated, in another farm in the same season maize is cultivated, the water requirement for both the crops is different. But if we try to communicate that they are going to receive this much water, it might be suitable for one region but might not be suitable for another region. But if we talk in historic context that what is the water used in this particular region and what is water available, so then you can always communicate in terms of anomalies, and that will be simple to communicate and will give a particular meaning in terms of impact in a particular cropland. So this I mentioned earlier that we can communicate in percentage of normal, deciles, or percentile, and so on. I'll not get into it. Another important issue on this drought indices is this, that there are two kind of indices. One is input based indices, the other is output based indices. Precipitation is one index which is input based index, but when we are talking about agriculture, so water is used ingested in the soil, and then as a function of soil and vegetation, then it is absorbed or transpired in the atmosphere. So precipitation, percentage of normal, SPI are one of the most used input indices for drought. Then ET and soil moisture and vegetation conditions are output based, which use the function, which is function of soil and vegetation, and then it is observed. So there are benefits and disadvantages for both the things. Input based index is simply to monitor, and then you do not need complex modeling for that and complex system. But then it might not be a good indicator for impact, while output based indicator are like a little bit complex to implement, but they are good indicators for impact on the ground or impact on the crops. Yeah, same input advantage, quick to compute advantage, uh, but crop, they are crop independent, but you cannot be crop specific, while the output based indicators are closer to reality but little bit complex to compute. So whenever we are setting up some drought monitoring system in a particular area, it is very important that we account the local climatology and we account the historic databases. So whenever we go somewhere and establish a localized drought monitoring system, we we uh, we account historic data, and then we aggregate them into some sort of administrative unit or functional unit, so that calculations can be monitored on those units on the regular basis. Like for example, this is a one visualization of one particular province in Pakistan, that how precipitation is happening every month, or how what are the vegetation conditions on monthly basis. And then when you have accumulation of historic data, and then you just run the recent conditions, and then you can have a good communication of situation, that what is happening in comparison to historic conditions, and what are the deficiency or excess of conditions in a particular region. So again, whenever we develop those systems, we try to also bring in some sort of visualization. So it is a large part of it is dealing with the observing the particular indicator, quantifying it, comparing it. But an effective drought monitoring system should also have a very like effective communication in forms of infographics, so that information can be communicated to wider audience to convey the severity of the situation. Coming back to this more like I'll not get into this too much detail of other variables, but one variable which is very common for drought monitoring is vegetation condition, which is based on optical remote sensing, which differentiate, which is a different measure of greenness between red and near infrared band. So when I'm just giving some examples from Afghanistan, that how precipitation deficit observed in 2018 is related to vegetation condition, bad vegetation condition in January to onward. So that like if you see that November, December, January precipitation is low, and when you see the impact, 2018 vegetation condition is very bad in comparison to 2018. This is like more simple index for looking at the drought conditions in a particular region. Then again, I was mentioning that for an effective drought communication, you need to have administrative boundary, and you need to aggregate that communication in a visualization form. Like for example, drought is mostly, if you talk about a particular province, and if you try to aggregate whole conditions within a province, there can be situation where there is good rainfall, but there can be a region where you have bad rainfall. But when you will sum them up or aggregate together, you might see a normal situation. That's the kind of con, uh, concern you need to maintain, that you communicate the area under good condition, area under bad condition, and that communication will be better to communicate it to the end users. Like for example, this graph is showing that what is the percentage of a province in bad situation, good situation, or so on. So that's very important. When you monitor a particular indicator, you also aggregate in a way that you don't lose the essence of the information. Look, why I picked up the NDVI as an example, because NDVI, you can monitor NDVI at continental scale with at 1 kilometer resolution, but you can also monitor vegetation conditions at farm level with the availability of high resolution satellite data in form of Sentinel-2 and Sentinel-1. Oh, sorry. In case of NDVI, it is Sentinel-2 optical data. So this is an example of drought conditions, this year's drought condition in Afghanistan, where in a particular area, wheat was grown in a large area, but due to deficit water, there's no wheat sown in large area. Like here for the, we mostly use vegetation in red color in our visualizations. So you see that you have a large area of under wheat, but here there's no wheat. And then you can also look at spatially, but also you can also draw some of sort of the graphs. Like if you know that looking at the phenology is very important for agriculture area monitoring or crop type mapping or presence or absence of crops. Like for example, this is an NDVI graph over a period of time that you have a higher NDVI value in the month of April, because uh, in Afghanistan, uh, March until March or early April, it remains snowy area. But then as soon as you go from March onward, you see the crop growth, and April is the peak time. In 2020, you had this crop, with this graph suggests that in 2020, you had crop presence in this area, but when you are looking March, April in 2021, there is no crop. So you can see it visually as well as calculate it arithmetically. Again, some example of comparison of situation at farm level from Pakistan, that 2018 versus 2017. 2018 was a drought year where people lost sowing of crop because of non-availability of irrigation water. And while in 2017, all those areas were irrigated and cultivated. Uh, in many of the cases, we look at the drought at administrative unit level, but when we are going into climate risk management and risk management tools like crop insurance, it has also become very important that we can also look the situation at farm level when we are giving compensations to farmer. So this is an example where you can compare different years and growth of crop status to look at farm level and ingest those kind of assessment in insurance processes as well. So I have been talking about one indicators at one point of time, but when we are talking about crop condition, there can be certain situation when during the peak season of a particular crop, the greenness is good, but it has several other kind of stresses. So those stresses can also come from precipitation, temperature, or so on. So it is important that we can also blend those uh, climatic and vegetation indicators together, and then apply those composite indices for drought monitoring purpose. So one of the drought monitoring indices which we tried is vegetation supply index, which includes the precipitation and temperature for monitoring vegetation conditions health. So these are the simple explanation of three indices, like we included VCI, temperature condition, and vegetation health index. And when we try to apply those kind of indices, like for example, this normalized vegetation water supply index, when we try to apply this index in a particular environment. Like for example, we have irrigated system and we also have non-irrigated system. When we are applying this in the arid system, we can see that vegetation is maintaining its moisture for longer period of time. Like for example, if you can see this cursor here, but in the arid system, it means that this maintaining moisture for longer period of time, that it indicates that it has some sort of water source in addition to precipitation. So while in the arid system, the vegetation is losing water supply very sharply. So these are the kind of indices which can give you a combined effect of temperature, vegetation, and precipitation. Again, when we are talking about this precipitation occurrence and its impacts on the crops, sometimes it's also very important to understand the ecosystem, that what is the lag time between the precipitation and vegetation condition. So what we have seen in case of uh, Nepal, that in the irrigated system, it has higher it has a lower relationship with the precipitation, and it has higher relationship with the in case of arid agriculture. And a lag time of between like 64 days is there between occurrence of precipitation and improvement and improvement in vegetation condition. So these are the kind of studies are important to look back, that what time of interval is important to look at the occurrence of precipitation and initiate some sort of warnings for the farmers. Again, we applied the same index in some of some region, mountain region of China, and there what we observed, that the effect of drought varies also in terms of land use. When we compare the evergreen forests, severe dry conditions, about 48 days, the cropland, then you can see that in case of evergreen forest, you have lesser impact, but you have more impact in form of shrubs and croplands. So in this area, these trees like walnut trees has more resilient to drought in comparison to cereal crops. So these were like some sort of scientific background on these indices and their application. So when you want to put some drought monitoring system in place, you need to engage with the local institutions, and then you need to customize the tools so that authorities can use that tool more effectively without going into the data processing and knowing all kind of complexities of earth observation or climate modeling. So what we have done during last 4 years time, that we have developed regional drought monitoring outlook system with special emphasis for Bangladesh, Afghanistan, Nepal, and Pakistan. So we engaged with national institutions, we looked at their requirement, and there are n number of indicators available, and then we synthesize with them that what are the indicators which are more important for those institutions to make their system operational. We look into the Earth observation data, satellite-based Earth observation data. We look its calibration or its effectiveness on with station data, and we have different, like for example, in case of precipitation, we have chosen CHIPS. CHIPS is one of the precipitation data which has historic time series of 30 years, and it is available at 5 kilometer resolution. We found this particular precipitation data suitable in our region, and what we found out that it has higher accuracy in plain in comparison to mountain regions. Also, it has higher accuracy in high rainfall area like in Bangladesh in comparison to low rainfall areas of Afghanistan. So there were like 2-3 kind of precipitation data sets available. In one of the inherent precipitation data, it was giving more accurate information for high elevation regions. But then it was closely matching with the river discharges, but it was not closely matching with the land-based precipitation station data. Since our primary application was agriculture monitoring and land-based information was more important instead of river stream flows, so we prefer to use CHIRPS data in our system. Now, with the current system, we have an operational drought monitoring system, which is taking account of soil moisture, ET, SPI, temperature, and NDVI, and it is available at 5 km resolution. And then there are some good user interfaces are also developed so that you can go to a particular district, and based on the agriculture mass in that particular district, it will give you the drought conditions and its impacts on agriculture. So we also have a seasonal outlook in the system. I will talk about that seasonal outlook separately, but during this time, I'll give an example of use of this national drought watch in case of Afghanistan drought condition. Afghanistan is going through severe drought conditions since November 2020. So through our drought outlook system, we initiated an early warning in October that it is likely to be a dry year in Afghanistan. So again, I mentioned earlier that all these drought patterns are driven by uh, Earth system and climate dynamics at Earth system level. Like this sea surface temperature in different regions affects the water movement. Like what was being observed by those climate system monitoring tools, that this year going to be a La Nina years, and in most of the La Nina years, Afghanistan comes under the water deficit. So based on this, we initiated early warning, but that was not taken, as we know that our operational system, government systems are not tightly linked to those warnings. There was not much preparation, but as we entered into February, March, it was being observed by the station data as well as remote sensing data. There is a severe deficit in rainfall, and about our preparedness on the use of drought indicators for societal benefit. In Afghanistan, about 70% of population is engaged in livestock rearing or pastoral system. So we also have a good monitoring system of our rangelands monitoring in Afghanistan. So when we started looking at the drought conditions, like for example, we particularly focus on rangelands, and then I am repeatedly mentioning that when we are talking about drought communication, it is very important that we communicate in a way that a decision maker can understand it simply. We have been communicating about the deficit in rainfall. Like for example, uh, this time drought. So I have some complication in here. So this is actually the year difference is like that. So sorry, no. I'm it is wrong. So when we were communicating our deficit in precipitation, it was not being taken very seriously. But in the last drought event, 2018, there was a relatively lesser drought, but there was a serious impact on the pastoral livestock. About 150 livestock lost their life during 2018. And this time, by the month of March, April, we started communicating in comparison to 2018 situation. And then that communication actually worked very well. That you have a worse condition than 2018 condition, and that communication was taken seriously. uh, and then in case of Afghanistan, it's very important that you can observe the drought condition uh, until February, March, but the real impact starts happening in the month of April, May, June, when vegetation starts growing. So most of the system is temperature driven. As temperature increases, then grassland growth starts, and then all this grazing migration for grazing starts happening. So you have a good lag time between the start of the vegetation and the observation of precipitation. So that you can see in here that even in many cases, this is a like a start of season observed by remote sensing. What happens actually that you can monitor grassland growth, and you can put time for that. You can measure the phenology. And here what we have done, that we are trying to communicate what is the start of the season across the Afghanistan. The start of season starts somewhere in February, and it in some areas like in Badakhshan, it goes even until the month of May and June. So that's the kind of like, and then again, it is very important that when you are measuring vegetation conditions in a particular time, it should be the start of the season. If you will try to measure current situation in comparison to historic situation, and when there is no vegetation there, you will miscommunicate. So we will in this vegetation condition monitoring, we are not looking at the areas where vegetation has not started. So then this when we are taking out this gray areas or black areas are the areas where vegetation has not started started its season. So we are only communicating about, like for example, in March you have large area which vegetation has not started, and then in April and June you have more areas which are where vegetation is there, and then these are the observed situations. Like in the month of May, you can see that this northwestern region is the most affected area. So that is also very important. When you try to put those vegetation anomalies blindly, you can also miscommunicate. And this has actually happened this season, that some of the institutions tried producing vegetation anomalies while accounting the seasonality or vegetation growth phenology, and those maps or those assessment actually miscommunicated, and which also which also made some of the government institutions reluctant to declare drought. So there was a long debate, and when this kind of communication was communicated, that it is very important that you look the local context. All the global indices will not be applicable across the world. Like for example, I mentioned that in most of the cases, land surface temperature is taken as stressor. But in case of higher elevation area, it is not a stressor, it is an enabler. If you will try to apply vegetation health index in Afghanistan, all the high elevation area which are shown in bad conditions will appear as good condition, because like LS in lower elevation area where vegetation precipitation is derivative for vegetation growth, uh, land surface temperature is a stressor. But when you go in higher elevation area, for example, in this region, more than 1000 meter, the relationship between LST and NDVI uh, inverses. So it is totally like with the increase in temperature, vegetation conditions is improving. So that's also important, that all those universal indices are not applicable across different region, and you need to be conscious of local context while applying those indices. So again, I'm like since most of our work is related to making these data sets useful or information useful for decision making, so we always put a lot of effort on communicating the severity situation or whatever like phenomena we observe. We try to communicate or aggregate into the visualization. Like for example, this graph on the left hand side is giving you two things. One is that what is the rangeland area, in a particular province, and what is the severity situation. So the size of the rectangle is giving the rainland area, and the color of that rectangle is giving the severity. Like for example, if I can say that Kunar province is in good situation, but if I only communicate Kunar is in good situation, it can miscommunicate that a lots of animals are not dependent on in this those rainland, because rainland area itself is very small. So then Kunar is becomes less relevant for those areas. Like for example, the Ghor province has the highest rainland area, and it has high drought condition. And similarly, Herat is another area where you have large rainlands, and they are again under extreme, intensely under drought conditions. So that's another way to communicate a particular, like we are measuring in this area, we are measuring the rainlands, we are measuring the drought severity situation, and then we are communicating those situation. So, like there was one point when we facilitated the government in understanding the severity situation, that situation is really bad. At another stage, we are also helping the government to particularly the pastoral sector, the rangeland division of Afghanistan Agriculture Ministry, that what are the areas which are extremely vulnerable, and what kind of feed, like by measuring the productivity and rangeland area and an animal size, what is the amount of concentrated feed required to give it to community so that their animals can survive, so that they can avoid the death of their animals. So that kind of calculation has also taken place, which is being accounted in the government planning process, and associate resources for that purpose. So I'll not get much into, like, just one precaution I want to give you, that I mentioned that whenever like those global data sets are available, they are not applicable across the regions. Like for example, one data set is used in this particular study where vegetation is measured, vegetation anomaly is measured without considering that you are putting a formula in an area where there is no vegetation. Like for example, in this sand dune areas, it is not possible to have the vegetation or grow the vegetation. So firstly, that putting this some sort of equation doesn't make sense. Then again, like I mentioned that by the month of March, those areas are under snow, while you are communicating the vegetation condition. So if you will put some formula on some values, you will always have some output, but that output will not have any relevance to ground. So that's very important, that when you develop you know those indices, you know that it is possible to calculate, you have some data, but always try to know the conditions, because sometimes your assessment can be extremely dangerous. Like sometimes they say that it is better to have no information than wrong information. So that was an example from the early warning perspective, and then understanding the drought severity conditions. The other thing we talk about is this resilience. So like with the use of these historic data and its impact, historic drought data and its impacts on the crops, you can also understand that what are the crops, what are the regions which are having more effect because of drought, and what are the areas where agriculture system is resilient to drought. For that matter, we tried to aggregate Nepal into different, like 4 cereal crops: wheat, maize, rice, millet, and we identified their major crop zones. And then we looked into the historic data and try to see that what are the areas which are under, what are the crops which are in a particular geography which are under extreme drought threat. Like for example, uh, if you look into this maize map, And precipitation for maize in the mid-hill maize is precipitation during February, March, April is important for this region. And we see that during this time period, the mid hills are under extreme drought conditions. Like drought frequency in this region out of like 30 years goes up to 11 times. So you have a maize grown area in here, and then the time of the maize growth where like precipitation is important is passing through extreme stress. So this suggests that this particular area require uh, drought resilient crops because here precipitation patterns are extremely stressful. Similarly, if we look into the paddy crop, paddy, the precipitation in June, July, August is relevant for those areas, and we are not seeing that paddy crop is under there is a pattern of stress or there is an extreme threat to paddy crop in case of Nepal. And similarly, like for example, if we are talking about wheat crop, wheat crop zone is northwestern Nepal, and there again during this period of time, historically we are not seeing too many of drought events. But in this particular uh, south, sorry, eastern region is relatively more under drought severity condition in terms of historic drought frequency. Similarly, we have seen that what is the production regression with the drought severity. We can see there are some districts which are like higher relationship. It means that they have high dependence on the precipitation and they are more vulnerable to drought. And there are certain districts which are coping, that they are resilient to drought condition and they have low regression values in terms of drought severity of 30 years period of time and crop production out of those 30 districts. So this kind of assessment also gives us understanding which are the geographic pocket which are more resilient to drought and which are the geographic pockets which are less resilient to drought. There should be an extension of this study, that understanding that if a particular district is more resilient, what are the practices which are happening and what are the drivers of those resilience. So this kind of like drought assessment can also give us understanding on resilience and ecosystem agroecosystem practices. So that was an example from a resilience side. And then uh, we have been talking about drought monitoring, but there are several benefits of drought early warning. If we can know about a particular disaster coming a season ahead, that can be really excellent. But we know that there are uncertainties attached to those forecasts. What we have done in our system, that uh, we developed a drought monitor system, that it means that we have a system which has a historic data set, and if we put forecast on that historic data set, we can have some value. So what it means, that like forecast depends upon initial conditions. So if you have a good initial conditions data set in the form of, I didn't mention that we have developed a land data simulation system, which is giving us observations. So if you have a good data set on initial conditions and you put forecast on that, you will have advantages in looking at the impact, especially for the indicators like soil moisture and ET. So if you have historic data and then you put the forecast on that historic data, you can have and then you have a 30 years database, that you can make benefit of that database, and then you can have better calibration for soil moisture and evapotranspiration. So what we have done, that we have used LDAS for optimization. We are looking into the sub-seasonal forecast, which is about 1 month to 4 month time period. And then we are also looking into the one particular decision, which is drought. So this, I'll not get in this. So this is how our system is working for using of land data simulation to put the forecast that you have base data like on watershed characterization, you have meteorological data coming from remote sensing, and then you have land data simulation system, which is like looking at the input, looking at the vegetation and soil functions, and producing indicators on drought. So like, and when we're talking about forecast, then there are like depending upon the different calibration of different climate models, we can also receive several initial conditions. So in this case, we are using climate models which are giving us 7 different ensembles, and then we are putting them on different initial conditions, and then looking forward and so on. Then based on those initial conditions and different ensembles, we will come across a larger window of possibility, that what is the potential seasonal soil moisture occurring in this area, or what are the potential ET occurring in this area. And then you have to look into this whole breadth and average values and communicate it further as a forecast system. We also know that like forecast has lots of uncertainty, and if we are giving good forecast, it has certain value, but if we are giving a wrong in forecast, it has implications. But if we are not giving any kind of forecast, it has other implications. Like for example, if we are giving a forecast for drought, and then event is not happening, so we will have implication that there will be some sort of interventions which might have happened, and some investment might gone in vain. But and also we also have implications on us as credibility for forecast. And then if the even happens, and then you have given the forecast, and that action has taken place, and that has saved us from the catastrophe. But if there's another situation that you forecasted but even did not happen, that's fine. Your preparedness investment gone waste, but still you have no losses. But if you have given the forecast and event has happened and there's no preparedness, it has this big cost attached to it. So that gives it's a delicate decision, that to act upon a particular decision or not to act upon a particular decision. But as we are moving forward, there are more credible forecasts coming in. Like for example, I mentioned that we generated the forecast uh, for Afghanistan in October. We communicated it to relevant entities. Like I can tell you like this, the early warning produced in the month of October was so clear that I can just read it over here, that a continued precipitation deficit during entire winter period in Amu Darya Basin and Upper Indus Basin, covering most of Afghanistan, may result in reduction in wheat crop cultivation, particularly rain-fed areas. A decrease in rainland productivity leading to deterioration in livestock health is likely. So this was sort of like a very clear communication, but we know that no action was taken place. And there was a when we reached into the month of April and May, there was a rush in terms of preparedness. So like if such early warning has been accounted into the institution's preparedness plan, there might have been a better management to deal with this catastrophe. I mentioned that there are several other examples of use of drought work, like for example, institutions like World Food Program take those assessments into their preparedness plan, particularly in case of uh, 2015 drought, there was a major catastrophe in northwestern Nepal. And based on these data products, World Food Program was able to get some additional funds from donors to help uh, the marginal farmers and communities in northwestern Nepal. So I mentioned that there are lots of good usages of drought monitoring system for different level of decision making. But then there are needs are more specific as we are coming across more serious climate related calamities and more uncertainties in the climate, and farmers are doing their practices based on their ancestral knowledge and stable climate systems. So there is a more need to for them to receive more information related to climate and its impact on their particular farmlands. So taking this work forward, making use of ICT technologies and observation technologies, we are developing institutional setup as well as technological setup to improve the ability of local institutions to communicate it to farmers about the impacts of climate forecast and on their croplands. We are developing mobile apps which are being used by which are planned to be used by agriculture extension staff so that they can communicate the agronomic conditions. And then we are putting dashboards and earth observation based data monitoring system to provide climate related information. And then we are also ingesting those package of practices within those advisory systems. So what is happening in most of the region that most of the time agromet advisories are generated in the central agencies, like in case of Pakistan, agromet advisory is being generated from PMD, but they cover entire country. So and then cropping calendars are different, local situations are different. As we are devolving the governance systems, we also need to devolve these mechanism, advisory mechanism. So these kind of ICT technologies are helping us to establish those new forms of localized advisory system supported by Earthobservation technologies and tools. I will stop here for a while. I don't know what is the timeline. So I will ask for questions now. Hello, anybody?
Vaitalji, there is one question. So I'm not sure if you can read the
Okay,
message box,
okay,
chat box.
okay.
Shall I read that?
Yeah. It's not visible to me. Let me. Yeah. Can you please read it for me?
Okay, sir, if we want to calculate the growth ratio of vegetation, which parameters we should use?
It depends. Like for example, if you are talking about growth of vegetation, greenness, NDVI is one, and we have exercise section separately where we'll do it. So you need to look at the NDVI, and then you need to then there are two ways to look at it. One is this. Let me go back to a particular slide, and then I can maybe explain it better. Okay, for example, this. Okay. So yeah. So this is NDVI. For example, like the vegetation starts in case of this Pakistan in a cropland. Vegetation starts growing somewhere in December. Wheat is cultivated in November, and then it reaches at the peak in the month of January, and then it comes back. So this is all vegetation. It has two elements in it. One is peak of season, that what highest NDVI value you are getting of a particular season. Then there is another value which is season integrated. You start calculating NDVI value from November till the end of season, somewhere in the mid of March. You aggregate it. What those regressions suggest, that season accumulated NDVI is a proxy of productivity. So you calculate entire season NDVI value. It is more related to yield. And in some cases, the vegetation health is in some certain vegetation systems. Oh, I think mic is open.
Hello, Mr. Faisal. I'm from
Yeah.
Afghanistan.
Yeah, yeah.
Do you have drought data? If you send Waidullah Yusufi, if you not send, then please share me with me.
Sure, sure, sure. I will definitely. Yeah. Some mic is open. So
Yes, now it's closed because that is from Afghanistan.
yeah, yeah. So like, so I was communicating the season integrated NDVI is one good measure to link it with the crop yield. But in some vegetation conditions, it can be the case that peak of the season can also be related to the yield. So it depends, like, yeah. But NDVI is like, and in terms of intervals, you can measure it daily basis, weekly basis, and monthly basis. And then again, you can aggregate them seasonally.
Thank you. There is another question. So how we can relate growth ratio of vegetation with the drought analysis?
So actually, vegetation monitoring is itself is a form of drought monitoring. The vegetation greenness is one of the indicators. So that what we are always interested in is impact on yield. In case of crops, we are always interested in evaluating yield. And for yield, I mentioned earlier that you can always develop regression on historic drought patterns and production. So then you develop some sort of regression value, and then you can use that. That you can differentiate. Like for example, if we are only looking at SPI and the system is irrigated, it doesn't make sense that you look at the rainfall. If you are getting water from another source, that will not be relevant. Then what variables you need to measure? Like if you ask me that one is in arid system, precipitation itself, SPI is a good indicator. But when you will go into an irrigated system, ET is one very important indicator. But if you want to develop a composite index, you can also develop composite indices. So you can apply SPI separately in one. Like for example, composite index can also be developed this way, that you are looking at the SPI, you are looking at the reservoir. Even you can develop an index on water availability in a particular reservoir. Then you can also develop ET anomalies or water stress, and then you can weight them, that in this region non-availability of precipitation water has little contribution. You will take its weight as 10 or 20%. But then you know that this reservoir water availability has highest contribution in this, like for crop cultivation and its growth. You assign a higher weight to that particular indicator. For example, in Tarbela water, if you want to assess crop conditions in Bahawalpur, in the month of April, you already know that what amount of water is available. So if you want to develop an early warning system, you can give a weight of about 70% to that particular indicator. Then again, you can also assign June or so on. You can also aggregate it. So monitoring indicator is a scientific process, but the decision or like the impact is the real thing. So in case of rangelands, it is simple. If you have a rangeland growth vegetation, most of the cases it will be available for livestock grazing. But again, there you also have an element of palatable species and non-palatable species. If in a particular area you have good vegetation condition, good grassland, but if those are not palatable, it has again implications. So like you can monitor particular indicators, but then you need to relate those indicators on ground situation in form of crop types or rangeland types or so on. So you might get a sense from my conversation that only remote sensing data doesn't give you complete picture, and sometimes it may also misguide you. So it is always very important whenever we are using remote sensing methods, we closely link our observations and assessment, and we try to triangulate it with the ground situation. Yeah. So I can just briefly demonstrate that what are those tools. Just a minute. Yeah. So I also shared this link in there in the text. I hope you can see it. So this is this particular system is mainly developed to look at the seasonal outlook from 1 month to practically 4 month period across the basins. So we mostly get information at country level, but sometimes for some regional perspective, basins are important to understand their conditions. So you can go to a particular basin. For example, you can select a basin or a sub basin. Like for example, I'm selecting here Indus Basin, and then I mentioned that in our system there are 7 ensembles that what does this mean? That there are, for forecasting, there are 7 different parameterization. So, and then we are looking into the average conditions by only selecting the mean. We can also select individual ensemble as well. So what does this suggest? So this particular forecast was initiated in April, and it tells us that in the month of May in Indus Basin there was a higher than average precipitation. June is almost average. July is much above average, and so on. Like then it gives 9 months forecast, but we may, as we go further from current time, the certainty of the forecast increases. So that we mostly suggest to look only until the 4 months. So we have generated this forecast in the month of April, but our new forecast is again in the process. So we will update this every 2 to 3 months time period, so that we can only look up till 3 months time period and so on. So that's about the regional outlook. Then we also have, for example, this is a national drought watch. So it has several functions. Like for example, you look at country level, you can look at province level, district level. So like for example, country level, so this is giving the information till June, that what is the current situation of soil moisture, precipitation or so. But what we can also, this was, so okay, like for example, so this is the current window. So you can look at the current, like for example, if we try to look at Jumla province district in Nepal, so we can see that how over period of time this district has gone through until June 2021. We our colleagues from Nepal must be knowing it that this time it was a severely dry conditions. This rectangle, this dot, black dot is showing us average conditions, and this blue is the current condition. So this is the situation so far in Jumla. In all of Nepal, we have higher than normal precipitation, but here we can see that in Jumla it is lower than normal. So this is also, these Earth observation also gives you some means to look at the some like remote areas which might be going through some different situation, which where the people sitting in the headquarters might not be aware. So even I paid attention to this today, and it's really like strange that one of some of the regions of Afghanistan are still under extreme uh, precipitation deficit in a particular region. So another thing which we can do is, like for example, I'm taking this example from Afghanistan, that you can do a seasonal aggregation. So it is not just every 10 day you are saying that you can make a composite of 1 month, 2 months, 4 months, 6 months. You go to a particular area. For example, I'm selecting here Ghor province. You go to a particular year, for example, this year, and I am selecting January to April. By the way, in case of Afghanistan, 80% of the precipitation happened between November to April. So I'm just like January to April, I'm looking at it. And if we calculate these things, we can see that March, like for Ghor province, all months were below average except March. So that there was a like above average rainfall in the month of March. But sometimes this a short period rainfall does not compensate for larger period time. If I only change the year here, for example, 2020, and I keep the months same, let us see what does it suggest. So it was a in sorry, I didn't check. Oh, it should be 2020. 2020. 2020. Core Core province in 2020 first April. So even last year it was under deficit rainfall, or what is happening? For example, if I take 2019, 2019 was an above average year. So the idea is that you can always go back to like 2001. You can always compare different months, different regions, and make your evaluation for your understanding on drought in those areas. So you have current situation where you are given the most recent, like for example, here we are looking at until June. Then you can select different time intervals. And one thing important to mention here is that in case of Nepal, Pakistan, other than rangeland area, they are all masked on the agriculture areas. So you are looking only into agriculture area. But in case of Afghanistan, you are looking both pastures as well as agriculture areas. So you can play with it, like this interface is available. Let me put all others as well, Pakistan as well. B BT.
Sir, I have a question. What is the resolution of these data sets?
5 kilometer. 5 kilometer. I mentioned it. 5 kilometer.
And can we use this data to make decision and provide info in local level? You know, their topographical or complexity.
No, that's why the last unit is district here. So you cannot use this data at farm level. The farm level data, like you can monitor conditions, but then you have to downscale those things. So that, like, then you have to bring people in this. Like, for example, I mentioned that we are developing an advisory system. So where advisory committee is there, they will look at this climate. It is not possible to look at climate data lower than that. It's very, unless you have station data. And then again, forecast is a complex thing. But what can you do that you can understand that that rainfall is more than needed or less than needed, or temperature, what is temperature conditions, and what is being grown in the crop. There can be good agronomy expert or crop experts who can link them together and convey the message to the farmer. But conveying this kind of data directly to farmer is not advisable. So there should be an intermediary person who should interpret this data in terms of crop. So I suggest, like, you can play with this these tools for a while, and we can stop here. Let me also put link for Pakistan. Bangladesh. Mhm. So any questions, please come forward.